should stop talking about management now. Okay, so basically project 3 is just building the test bench with the sense amp in it. You're going to build a module for the sense amp and put the additional pulse sources in. You don't have to actually get the simulation running. Let's see who dinged in. Elizabeth already got, Luke I think I've already gotten, and Josh. Okay. What? Yes. Okay. Then what else okay, then we get into some other stuff. Well, Flash will come after this. So on Thursday, we'll start Flash. Today is mostly about how we get the threshold voltage of a MOS transistor. We've looked at the physics of the MOS capacitor and how the bands look across there. If you go through the version of the slides that's posted on BB Learn, you'll notice that there's a whole bunch of solutions on there that give you equations that are helpful on your homework. You may want to look at that when you're doing homework 4. So we want to find out what kinds of things influence the MOS threshold voltage. If we know what influences it, we can change it. We can lower it for our smaller processes so we can get lower voltages on it for like 3 nanometer processes. And the 5 nanometer process, which they will be doing at TSMC in Northwest Phoenix. This is a portion of the periodic table in case I need it. A reminder, a volt and an electron volt are pretty much closely related. The difference between the two of them is a volt is a joule per coulomb, and a coulomb is a large amount of charge, and an electron volt is a joule per the charge on an electron, which is a very small amount of energy. So this is an electron volt, is a much smaller. When you do those calculations, a lot of the calculations come out. When you divide by Q, or when you multiply by Q, when you divide by Q, you're going to get it in one set of units, and when you don't divide by Q, you'll get it in the other set of units. The magnitude of them will be the same. A MOS structure, it's made out of a gate, which is metal or poly. Which is polycrystalline silicon, which is is fairly conductive, not as conductive as metal. Then there's an oxide thickness, and then I have a substrate. So this MOS structure, metal or metal oxide semiconductor, looks like a capacitor. And what we did last class is we drew the bands going through that MOS structure. Now what we want to do is find out what contributes to threshold voltage and what causes that annoying body bias effect in 37 slides. So when we look across this MOS structure here, so here it is up in this little diagram up at the top. I've got the metal. Oh great, is this thing hanging up on me again? Draw. Oh good, okay. I was hanging up all during class. I couldn't draw. What?
No technical difficulties.
So far. No technical difficulties so far. Okay, so I've got the metal, I've got the oxide, I've got one region that's doped lightly, another region that's doped more heavily. And in order to draw the bands, the convention is I allow the Fermi levels to line up across here. And this is the Fermi level right here. I keep that as my reference level. So all the other bands are drawn in reference to the Fermi level. So what I see here, I see this big barrier right where I have the oxide. And on the other side, I have the metal. And then on inside the semiconductor, I've got one region of doping and another region of doping here. And I can see that the bands bend a little bit. Now the goal is to turn this transistor on. I've got to put enough energy on this side to accumulate charge on this side to make the bands flatten out. We call this the flat band conditions. Basically, the flat band is when I have that inversion layer right at the gate on the semiconductor side of the gate. I have that inversion layer there, so I definitely have a channel. So this flat band condition is related to what it takes to turn on the transistor and related to the threshold voltage. Okay, so this is what I want to do. The big barrier right here is the oxide. And I can control what's going on the other side by the capacitive coupling. I'm going to, if this is an NMOS, I'm going to get positive charge here. The negative charge here can bend these bands. If I get enough negative charge here, I can bend these bands and cause it to look more flat across there. Okay. Here we go. This is the MOS structure. Now I've got, this is the oxide right here. The oxide. Here's the MOS structure. Here's the charge distribution. Now I've got a lot of electrons in this region right here, because this is an N, this is an N-type sub, it's an NA. I've got, oh, this is the depletion region, never mind. I know it's called. Sorry, my mind is elsewhere. This is DR, stands for depletion region. In the, it's a P-type substrate, but in the depletion region, well, just like among a PN junction diode, the charge inverts, and I get a lot of electrons in the depletion region near the gate. And this is modeled as a uniform charge. So this is charge versus distance. I have kind of a peak in negative charge right here. This is when the inversion layer has developed, and I've attracted a lot of the negative charge towards the gate, as this is the charge that's charging up the capacitance of the gate. So I've got positive charge due to a positive voltage here that attracts a lot of the negative charge directly next to the gate. So I've got a charge profile that looks like this, kind of a point source near the gate and an even distribution through the depletion region. And then I go into the bulk and it's charge neutral. So I integrate this, and when I integrate charge, I get electric field. I see the sudden buildup of charge due to this kind of like point source of charge, and then a slowing and going down across there. That is the field distribution through there. Okay, I integrate electric field and I get voltage. And when we integrate this, we get a curve like this. So I have a voltage pretty much close to the gate. And this voltage that we get here is the voltage between the gate and the bulk, or the gate and the body. And there's some minimum voltage here that I have to overcome, which would be V flat band. That's not in that diagram, but I sort of. Okay. So we go to Gauss's law. There's two regions of charge here. There's QD, which is the charge in the bulk, and QD is going to be the charge on an electron times the number of the doping density I have in that region times the width of that region. That will be the total amount of charge that I get during there. And if I plug in my equations for XD, I can come up with this equation right here. It's not really a derivation, but it's about the best I can do in an hour. The other contribution to the charge is going to be the charge in the inversion layer right next to the gate. And that's going to be like Q equals CV. So it is the capacitance times the voltage. And the voltage across that is going to be whatever the voltage is between the gate and the body, minus the voltage it takes to bend those bands up and flat band them, minus the work function, plus the rest of this charge. Phi D is the total amount of charge that I've got there. Okay, we can create this parameter. This is the definition of gamma. I'm going to define the parameter gamma to be what it takes to simplify this equation. Basically, if I want to, I would have to divide by COX to get it inside the COX, and I would have to multiply it by the rest of this stuff. So this is just a simplifying parameter to make it all in terms of phi s. So that is the total charge accumulation that I have there.
So when you calculate gamma, with that you can calculate gamma and be able to actually utilize gamma.
Yeah, with that you can, once you know something about the process, when you know that you're using silicon, you could use epsilon of silicon. If you're using germanium, no, you wouldn't use hafnium as a semiconductor.
Oh, right. We're talking about semiconductors.
We're talking about semiconductors.
Not
So you could use silicon, you could use germanium, you could use NSP, you could use gas, you could use whatever you want there. But for most purposes, it's silicon, which is 11.7. But you could see that this gamma would change with material because of this. It changes with the doping density. The rest of this, the Q is a fundamental fundamental constant of the universe, so we can't change that, and we can't change epsilon naught. We can change C oxide. C oxide is the capacitance per unit area of the MOS device. So it is epsilon ox over T is what COX, what they're calling COX prime. So I could change COX by changing the material of the dielectric, going from silicon to silicon dioxide to hafnium, whatever it is.
oxide,
Yeah, it's more than just hafnium oxide. It's nitrated hafnium oxide. I just did this in 280. I can remember that. Okay.
So that's the epsilon of silicon, like that silicon is the subscript, right?
Okay, so for COX, it's the epsilon of the oxide. For SI, it's the epsilon of the material of the semiconductor. So they're different relative strengths there. And the other thing I could do to change COX is, of course, make the oxide thinner. People are trying to increase the capacitance per unit area because the area is getting smaller. And the way they do that is they make the oxide have a higher dielectric constant and they make the thickness smaller. Okay. And that is called the body effect parameter because it's going to influence the body effect part of this. Okay, this is with no body effect. Now, phi s is the surface, and we talked about this in the last class. It's that one slide that kind of will help explain all the bands in it. Phi s is the surface potential voltage at the oxide silicon interface. So it's a function of what materials you're using, which oxide you're using, which semiconductor you're using. That is going to determine phi s. You don't have a lot of control over that. They're going to tell you what oxide to use because you need a higher COX. At strong inversion, this is the definition of strong inversion here. That means I got enough electrons accumulated to form a channel at the gate. We have enough voltage here to get the potential there. That's going to give you V flat band. V flat band, looking at this equation, is going to be phi s minus 2 phi f. Again, they're functions of the material properties. You can't do a lot once you get the numbers from the material. The V flat band is going to be an integral part of what's going to contribute to the threshold voltage. And it's very much a material property. This is where engineering morphs into physics, morphs into my less familiar cousin, material science.
You're making more to material science class.
Yes, it's applied physics and material science. I may be forced to take some of those. The surface voltage at strong invert, I don't see anything in there I really want to talk about. Where does inversion, oh, this is important because this is, it's easy for me to say this in 280 without having to explain a whole lot to people. Where does the charge for that inversion layer near the interface come from? If I just have a MOS structure right here, what I could do is I could go down into the bulk and I could generate electron hole pairs, or I could generate electron hole pairs down in the bulk. And most people, that's kind of like the first place they think that that charge comes from, is I'm generating electron hole pairs in the bulk of the semiconductor, and then those electrons are being electrically attracted to the other side of the gate by the voltage at the gate. That takes seconds to happen. If we had to wait seconds for a transistor to turn on, we'd be waiting hours for our Zoom feed to come through. Okay, so that's not really what's going to happen here. What?
Everything running on dial-up, essentially.
Probably worse than dial-up.
Yeah, actually.
Yes. I remember dial-up. You guys don't remember dial-up.
Dial-up.
Okay. Okay. We were in California. That was like 2000 or so, 20 years ago. We had dial-up. But there's a more convenient place I can get charge from. Now, this is a P-type substrate. This is an N-type diffusion right here. I have a PN junction between the substrate and the source contact. So there's going to be a depletion layer around there. Since this is N+, most of the depletion width is going to be in the P-type substrate. So this depletion region on the P side of a PN junction will be mostly electrons, which forms a great source of electrons to get the inversion layer at the gate. This is really fast. This I can do in femtoseconds. Fortunately, that PN junction is there, forming the depletion region, so that now we don't have to use sub-dial-up speeds on our internet. Is the general conclusion. You may not hear completely the discussion that's going on in the class, but it's at least there's a discussion going on in the class. It's not me just babbling.
Babbling incoherently into the nightmare screen.
Into the nightmares. You know, this is good because Zoom's getting ridiculous again. When we first started this, Zoom was so ridiculous that I had Oz the Great and Powerful in my class. People were randomly renaming themselves and putting.
We've got iPad 2 again.
You know, there's iPad 2. Okay, let's see that's.
iPad 2, Zoombot 367.
We've got to make Zoom ridiculous again so we can go back to the real world. Okay.
You can't normalize Zoom.
We cannot make Zoom our life, yes. Okay. Now we got two different conditions here. I've got my source and my body tied together. They're both at the same voltage. Oh, great. Oh, no, it didn't. They're both at the same voltage. In that case, my phi s equals 2 phi f. So this is phi s. This is due to the dielectric, the work function there. Phi f is the difference between the intrinsic Fermi level, the halfway between the band gap, and the actual Fermi level that I have changed through doping. You get to calculate this in the homework. So that's what phi f is. The band's been pretty much like this. Now, in order to overcome that and get flat band conditions, I've got to put at least a voltage of the difference between the two across there. I hope I'm making sense on some level. They're making sense to me, and nobody's asking me questions. So, if I increase the source to body voltage, my source is no longer at ground. My body still is. Then the amount of work I'm going to have to put in there to make these levels line up, these bands bend down further, I'm going to have to put more energy into the system in order to cause that strong inversion. So pretty much what I said, for those of you who are looking at me with a funny look on your face, pretty much what I said is, if I put a body bias across there, I have to put more voltage across the gate in order to overcome this barrier. The flat band, the whatchamacallit, the flat band voltage, no, not the flat band voltage doesn't increase. The threshold voltage will increase. I have to put more energy into it if I have a source to body voltage, non-zero. Okay. I think I'm perplexing some of you. It's me too somehow.
Everybody needs a little bit of reflection.
Yeah, it was like, it was really clear when I was in my office by myself and going through all this. And then suddenly I'm trying to explain it and it gets a little bit harder. What? Perplexion? Did I just make up another word?
No, I think I might have just made a word.
Okay. So in order to overcome, in order to overcome the energy at the barrier, so that I can create the inversion layer, the minimum amount of energy I need is 2 phi f minus VSB. I rearranged the slide a little bit today. We've got an expression for the total amount of charge at that barrier. We've already kind of figured that out. I'm going to rearrange it a little bit. I'm going to take this Q term right here. We decided this was gamma. It was gamma times 2 phi f. We're going to include the effect of the body to source voltage in there. And that's the charge at the surface. At threshold, when I'm starting to form the inversion layer, the charge at the surface is going to be 0. And then the inversion layer can form and I can get more negative charge there. That's true. This equation right here is always true. VGS equals VGB minus VSB. Everybody see that equation right there? Okay, because all that is I've subtracted VB from here and I've added VB right there. So that's always VGS. So I'm going to replace VGB in this equation with VGS plus VSB. Now, if I have a 0 source to body voltage, that goes away. And it looks like I had, okay, so this is the next step. So I assume there's zero source to body voltage. All I've done is I've replaced VGB with this expression right here. The next step is to ignore VSB and solve this equation for VGS. And what VGS is, it's going to be the VTN0 that I need to get the start of strong inversion. I could, since this is going to be equal to 0, Cox and the negative sign can go away, and I can solve this for VGS, and I get V flat band plus 2 phi F plus gamma 2 phi F VSB. That's the equation we were using in 380, and it's kind of where it comes from. Skipped a few steps on the derivation, but it gives you a good idea. Okay, I want to change the threshold voltage. We're going from a 5 nanometer process down to a 3 nanometer process. In order to do this without letting the smoke out of the chip, we need to lower the power consumption per unit area on the chip. In order to do that, I've got to lower the supply voltage, 0.8 volts, maybe down to 0.6 volts. Okay, if I'm doing that, I need my transistors, my NMOS and my PMOS, to have small enough threshold voltages down to maybe like 1 to 2/10 of a volt. I need to decrease the threshold voltages in order for this circuit to work at lower voltages. How am I going to lower the threshold voltage? This is where the engineers come in. They look at this equation and they say, okay, I can either lower V flat band, and we'll throw that one back in terms of material parameters. I can lower phi F, or I can make sure that no one ever puts a source to body voltage across the device. And I can make this gamma coefficient lower. So it's a lot of the processing is involving games of materials and doping, mostly doping, in order to lower those threshold voltages. Where the heck am I at? Protest. Sorry. I'm just, no. I just random thoughts are going through my head. So we got this expression right here. We know this piece of it, V flat band plus 2 phi F plus the gamma 2 phi F, has no bearing on what the source to body voltage is. This is the number that I call VT0 that I put in my data sheets. This is the 0 source to body voltage, threshold voltage. How can we, no, I'm not there yet. Okay. The gamma influences how, if I have a small gamma, I'm going to have a smaller effect for the source to body voltage. So the general term, we could write that, this is the equation you used in 380 probably. The actual threshold voltage is going to equal VT0N plus gamma times all that. Another thing you're going to need to make sure of if you're a processing engineer down at TSMC is you want to make sure that if someone puts a transistor in a circuit where it has a large VSB, will it be enough? Will this effect be small enough that I can still turn the transistors on and off reliably? So that's another piece of the engineering there. Yes. This is where you go back to your physics book and you start digging through equations and try to figure out how I can fix this. What? It's just, well, it's not, this is applied physics. It's like what I did with Maxwell's equations. I never liked solving Maxwell's equations. But there were a lot of people who did, and there were a lot of textbooks that had solutions to very specific Maxwell's equations problems in. And I would dig those out and I would look at the solutions and I would use those to build things. This is kind of the level that you'll be doing when you're working. You find somebody else who has relatively close results to what you're looking for, and you start figuring out, okay, how can I influence this and make it work better? Yay, Susan's actually here.
Susan's alive.
Yes. Okay, so that's kind of the way I understand this thing. Is I maybe not, I can go through and do the derivation, or not do the derivations. I can understand the derivations when I have to, but the biggest thing I'm looking for is the results here. And how can I influence the outcome of the results? That is when I have my engineering hat on. Okay, we've got three things here. We've got a gate, we've got an oxide thickness, and we've got substrate doping. Which one of how do these things contribute to the threshold voltage? I went around here and I included the equation for V flat band, because you can't just say, oh, change V flat band. If I want to change VTN, the things I have to deal with are this phi s, and that's going to be a function of doping. I've got phi f, which is going to be a function of this material, the oxide material right there. I've got gamma, which depends mostly on doping and materials. There's not a lot of handles that I have on this. What I would do, if I really needed to do this, is I would go through and create a table, maybe like in something like Excel. Given my relative doping levels, go ahead and calculate what phi s, what phi f are, and what VTN will be, and find that sweet spot when I get the right threshold voltage that I need, and I haven't messed anything else up, like made degenerative doping. Yeah, degenerative doping. Okay, so let's, okay. The rest of this class is going to be looking at pictures of things that I don't know anything about. Okay. Okay. There is someone in the department who understands processing way better than I do. If you want to learn about semiconductor processing, I would take Daphne Chen's class. If you want to learn about circuit design, you stick with me. But we're going to talk about some little processing tricks here. And it's just to give you an idea of how the processing works. I don't think Susan knows her camera's on. Okay. There's a couple of different ways we can do this. Okay. This is a bad way. Let's talk about the bad way first. Oh, great. I'm just doing this again. I can use my finger still. No, not yet. Okay. Now I can use my finger. Okay. If I put the active areas down first and I put the source and drain diffusion in first, then I put the poly down on top of it like this, what's going to happen? They're not going to be perfectly aligned. There's going to be some overlap between the metal and the poly and those diffusions. This is going to lead to capacitance, like we saw, that field capacitance like we saw in 380. There's a better way to do that. If I put the gate down first, and then I put the N plus diffusions in, and basically this gate blocks the N plus from being, from actually getting into. So I bombard the whole thing with electrons or ions. We're doing it in a different order.
Yeah.
If I put the N plus in, if I put the gate in there first, then the gate blocks the N plus from diffusion and they line up perfectly. Yeah, there's lots of little processing tricks like that going on. So basic CMOS technology. This is an N-channel transistor that's actually built in a P-well. That way, instead of relying on my N-channel transistor being in whatever the substrate doping is, I can give it its own doping. So I can control the doping that way. That's important for controlling the threshold voltage. We just learned that. And I put the P-channel devices in an N-well. Sorry, I'm drawing with my finger. Am I going to randomly hit buttons until this works? Oh, I think I know how to do this now. I do this, and then I say draw, and sometimes that works, and no, it doesn't. Okay, so I'm going to go back to just drawing with my finger. So we can put those in there too. Other things we need that field oxide to separate the transistors to keep them from talking to each other. We need diffusions for the drain and the source on both the N channel and the P channel. And we need contact up to the higher metal layers. Oh great, this is finger painting.
Oh boy.
These are the metal layers up there. So we need some kind of contacts up through the layers, and we'll deposit those layers one by one. Making more sense than I thought it was when I first looked at these. Okay. So this is the part.
Only happy little accidents.
Only happy little accidents. Sometimes it works, sometimes it doesn't. I've got my P- substrate, a lightly doped substrate. I'm going to put an N-well in. What I do is I put some kind of mass down that creates a layer called photoresist, that when I put the phosphorus, I put the whole thing in an oven, and I put phosphorus in there. It's a very hot gas at high temperatures and pressures to force the phosphorus into the substrate. Places where there's photoresist aren't going to get that's going to block the phosphorus from going through. So I can get the N-wells only in the places that I want the N-wells. And I'm not going to go into the details of how that works, because that's when it would get to be, it's better to talk to Daphne Chen. I'm the circuit version. I'm the device theory person. I'm not the processing person.
Question for you at end class about that.
You can ask now too, might as well.
Okay, yeah, I just wanted to ask if you had a way of checking if Daphne's teaching the 599 semiconductors class next semester.
Probably not next semester. I'd send her an email.
Well, because it's listed on Libby.
Oh, it is?
Yeah, it's listed on Libby. Right
For
now.
fall?
Yeah.
Okay, sure.
Yeah, I was just curious if it was Daphne teaching it or.
It would only be Daphne at this point.
Okay.
Because everyone else has gone over to the physics department.
So I'm gonna send Daphne an email about it.
The entire micro, I'm sorry, we're all physicists now.
I think mission to be part of that class.
Send Daphne an email and yeah, tell her that I recommend, just tell her you took memories and that I said you were okay. And you took Dr. Campbell's class, so you must know something between the two of us.
I hope I know something.
Yeah. Okay. Now I want to create the P wells. So for the P wells, I need boron. What we're doing here is we're growing a thick oxide over the N wells and a thin oxide over the P wells. Growing silicon dioxide on silicon is amazingly easy to do. You just leave it in a room and it will oxidize. Controlling the thickness is a whole nother thing, and I don't know how they do that. But there's a thicker oxide. Wow, it's working. There's a thicker oxide over the regions I don't want P well, and there is a thinner region that the boron can penetrate where I do want the P well. All of this is chemical, materials, engineering, processing. Yeah, I wish I could have. I don't know. I was still a device theory person. Okay. The absence of Fox is active. That's the definition of active area. I don't have a thick field oxide. Where I have active area, is where I can actually build the transistors. So what I want to do now is I want to put this masking layer on here pretty much to have a thick blocking layer down here and a thick blocking layer down here. And then I'm going to grow the oxide every place that the blocking layer isn't. So this is going to become my Fox right here, and this is going to become my Fox right here. And the Fox is acting as an insulator between the P wells and the N wells to keep the P transistors and the N transistors from talking to each other, and the individual transistors within the N well and the P well from talking to each other. It's what gives you electrical isolation between the transistors. Again, I'm talking about this in terms of what the transistors are doing and why you need this, why it needs to work like this. I don't know, yeah. I know why it needs to be like this. The how is like voodoo, black magic material science stuff. I actually did kind of take a class in this, one class a long time ago. What?
Bird's beak, excuse me.
Bird's beak, yes, that's a real technical term here. What the bird's beak was when I grow this Fox, so I've decided where I want to grow the Fox here. And then the Fox creates a bird's beak. The Fox is every place that I allowed it to grow, and now I can't write. That's what was going on yesterday. The Fox is every place that I've allowed it to grow. I have a thinner layer of oxide in the other places. Now the transition from the thin oxide to the field to the thinner oxide to the field oxide to the Fox is not an abrupt transition. There's a gradual change here, and it kind of looks like the little bird's beak, and that's what they call it. That's the technical term here, is bird's beak. Okay, that's not a good thing, because it causes my transistors not to work quite as well. There's some leakage in there. And the Fox should not have you need to keep the Fox away from the bird's beak. Okay. I'm telling you everything I know about processing. Well, actually I did. I calculated diffusion constants and how long you have to keep it in the oven and to get such and such a doping density and all that stuff. But that's been 30 years and I haven't used it. The next thing I want to put down here is I got the P wells and the N wells. I want to put down, oh wow, it works now. I want to put down my poly gate. That thin layer of oxide is acting as my gate oxide right there. I put the poly down and the mask looks like it's inverted. I want to put the poly down every place that I have a light line. I have a heavy line there. So I'm only going to concentrate it where I want it. Photolithography, you can make a mask that's actually a physical mask that's the same size as the IC, and you cut little holes in it to show where you're going to put the poly. Okay, now we're going to talk about Micron for a minute here. Micron is one of the few places that makes their own masks. And if you think about it, if you have a 9 nanometer process, your masks have to be exact and perfect at a level smaller than 9 nanometers. Because if my feature's 9 nanometers, I can't have 9 nanometer imperfections in them. And the masks have to be perfect. I mean, if you accidentally have a hole that shorts one device and another in your mask, none of your ICs work. And this is across millions of transistors. So we actually got to go in the mask lab at Micron. There was a level of precision engineering physics in there that was astounding. I haven't seen that in a long time. These were the guys that everything was perfectly precise. And they actually had ways they could repair small defects in the mask, because it would take them 6 months to make a mask set from what I see. And when they transport them, these things are so valuable that they actually have the guy with the handcuffs, you know, the briefcase handcuffed to the mask set. They send a courier with the masks over to, I believe it's Taiwan or wherever that, no, Singapore. I know that because whatchamacallit got a job over there.
The Mystic briefcase.
The Mystic guy with the briefcase to take these things. And these are really valuable because it takes months to build them. And they're one of a kind and they're unique. And all they are is pictures of where I want to put the poly down. And of course now it doesn't work. Where I want to put the poly down and where I don't want to put the poly down. And they have to be more precise than what we're actually doing. Amazing pieces of engineering here. And thank goodness this is almost over with.
Only 25 minutes.
No, I'm looking at only like 7 more slides. Okay, so I've got the poly there, and then every place that there isn't poly, I'm gonna put a photoresist over the P channel devices. So I put a photoresist over them so they get blocked. I put this in an oven with hot, high pressure phosphorus. It won't go through the poly, but it will go through that little layer of oxide right there and create N+ diffusions. Every single step of this process has got to be thought out and done exactly and calculated. And there's a whole gaggle of engineers and physicists and chemical engineers doing this. Another person who knows, do you guys remember Andy? Used to teach EMAG, used to teach 325.
Andrew Chrysler?
Yeah.
Oh yeah, I remember Andrew.
Okay, he used to be a chemical processing engineer at a semiconductor manufacturing plant. And so did Delbert Willey.
Did he?
Yes. Random people you can talk to if you really want to know about this stuff. You get a job at TSMC, what they will do is they will send you for an 18-month training session in Taiwan. After you get back from that, I would recommend going to ASU and taking some of their processing classes, just so you can keep ahead of the curve and learn this stuff. I look at the pictures and I know what's going on. Okay, so now I want to photoresist the N channel side, and I'm going to put arsenic in here to make the N+ diffusions. So again, it's just step by step. You've got to think it out. And this is probably not how they're doing it today. This is an older version of it, but it gives you a general idea of how many steps you have to go through and how exacting this is. Then I have to mask off the P side and put the boron diffusion in for the P+ diffusions. Now we're still not done yet because we've made all of our transistors, but none of them are connected together. Okay. So the next step, first of all, okay. One problem with silicon systems is if you leave them, you got to leave them in a vacuum chamber. If they're in air, the oxygen will oxidize the surface. So in order to protect them from that from happening, they use something called, and it works now. It's this pen that's driving me crazy. Solicitation. Yeah, it is.
Is it? No,
Your basic,
no,
okay, or a lot of times people just call it passivation, which is easier to say. What they're doing is they're putting this thin layer of titanium over this whole thing to keep the oxide from growing. They're basically putting a thin surface layer on top of all this to keep it from oxidizing.
And what, do they take it back off?
No, they do not take it back off.
It's
They're
just
going to
there.
form the next process here. All the transistor workings are internal. This is titanium is a metal, so it's like a metal contact above the poly. So it's just shorted out, though. It just shorted to the poly, so it's okay there. Metal over field oxide, well, it's maybe we made a little capacitor someplace, it doesn't matter. But this is going to stay there. The next step of the process is to put the metal layers down. And these are going to be like, I'm going to put like metal plugs through here. I can't draw them really well. And then put metal layers in here to contact to them. And there'll be better pictures later on. But that is metal connecting to other metal. So again, it just makes contact. And it just protects the surface. Now, one thing that was horrible about our IR arrays and astronomers in general is they did not like passivation, partially because the IR photons would not go through it. So we had to leave them all bare. And we had to keep everything in a nitrogen-filled tank when it wasn't inside a vacuum chamber to keep the oxide from growing on it and handle them quickly. And we took them out and put them in the air. The technicians couldn't handle the nitrogen environment, unfortunately.
How long is this entire process? Is it like a couple of days? Is it a month?
It's months. Yeah. Because you have to go through, first of all, you have to go through and create the end wells. And that's going to take, like a day or two. And then you've got to let them cool down and get to ambient and then go into another chamber where they're going to do something else. Sometimes you can do multiple steps in one machine, but still it's going to take, when I was calculating diffusion constants, a lot of times like one step of doing a diffusion would take 8 hours.
I'm assuming that like as the processes are going on,
Right.
like the next batch can be shuffled along.
Yes.
The process, so that things can be constantly churned out.
Yes, exactly. So the way the factory line works is you get wafer lot number 1 through machine 1. And then you have a robotic arm come down and pick it. You don't want people in there; they're too dirty. You have the robotic arm come down, pick up that lot, and take it to machine 2. At the same time, another robotic arm is picking up the bare die and putting them into machine 1 to start the processing. So those machines cost hundreds of millions of dollars. You want to keep them occupied 24 hours a day. And if one breaks down, you get to learn the fun of managers jumping up and down. So next thing we have to build is we have to build the metal contacts that are going to connect my transistors together. So I need a contact down to the N+ region, and I fill those contacts in with metal. Again, I need another mask that tells me where to put the contacts and where not to put the contacts. Every place where it's not blocked will be contact.
And those contacts are made with tungsten, so that I'm assuming that they're
Right.
withstand a very high amount of heat.
Yes, and the other thing, you need good stability because they have to they just So your machine.
What are the masks normally made of? Like or how do you know?
The masks have to be made they have to be made out of a material that will withstand being bombarded with tungsten at a high temperature and pressure without allowing the tungsten to go through.
Is that why there's that titanium layer that you saw like the slides?
No, the titanium was for passivation. Okay. So I don't know exactly what they use now, and I don't know, but it's got to be pretty sturdy stuff, because this is going to be coming in at maybe like 800 degrees Celsius at a high pressure, and it's got to be able to withstand that without allowing any atoms to go through.
Tungsten.
Yeah, super tungsten.
100 degrees Celsius.
What?
This is like 800 degrees Celsius, but if my computer overheats just a little bit, it turns off. Great.
Well, yeah, because then
It's gonna start melting.
Well, it's just melt it like this again.
you have to melt it correctly under controlled circumstances.
It's expensive.
Oh, tungsten.
Tungsten.
Okay. And I throw this in because this looks inverted to me. The mask looks like it's masking out every place I want metal one to go. But pretty much I'm putting a metal layer to make contact. It's contacting between contact over here and contact over there. So that metal layer is creating an electrical connection between those two contacts. And I put it in the places I want it, and I mask it off in the places that I don't. And then I put in more contacts, more tungsten contacts, a second layer of metal. So these are built, and I'm frozen.
Frozen. Yeah.
These are, I got 15 minutes. I will be back. For Susan's frozen too. Okay. These are built up layer by layer, like I'm building up floors. The contacts are like the stairs between the floors, and the different metals of layer are actually physically at different elevations, at different heights above the transistors. I will be back shortly.